Let me share my screen. And today I want to present my joint work with my PhD student King Song Wong from Jilin University, Chengchun. The motivation of of this work is following. We already discussed it several times that one of the wide distributed mathematical models for long polymer is a trajectory of a random process. And the most popular and most well studied model is the trajectory of Brownian motion. This model is called free polymer model, and free because of there are no attention to self-intersection. So, for example, if we consider long polymer on the flat, then in this model, it must have self-intersection, which is not natural actually for a real polymer. Why people study Gaussian models? Because in long polymer, there is such a notion of correlation between different pieces of the molecule, which reflect the ability to make turns independently, physically independently one from another. And this correlation is much easy, understandable, and can be modeled when we use Gaussian. But from other side, the shape of trajectory of such well-studied process, for example, as Brownian motion, is very complicated. So the question naturally arises the following. When the modeling trajectory is non-smooth, how to characterize its complexity? For example, we cannot, even if it has if we allow self-intersection, then we cannot use usual tools from topology based on some polynomials, so on, because such intersections we will have a lot, continuum set. So we need something else, and one of the possible way was already discussed there, and it looks like follows. We try to inscribe into trajectory of a polygon into trajectory of our random process, which model the polymer. This trajectory is drawn by the red line. We try to inscribe a polygonal line of the fixed shape. So what does it mean inscribe? It is understandable from the picture. The vertices of this line must belong to the trajectory. So we have such an idea. And maybe the more complex polygonal line can be inscribed in the trajectory, then the more complex is the shape of the trajectory. This is just one of the ideas how to try to say that, for example, this non-smooth trajectory is knotted and so on. So the question is, to find probability that fixed polygonal line can be inscribed or almost inscribed into a trajectory of a random process. Why I am saying almost inscribed and what does it mean? Almost inscribed means the following, that we have our polygonal line and we draw such a small balls of radius epsilon near the vertices of this polygonal line. And we just ask that our trajectory does not hit precisely the vertex, but just visits this ball. So we are looking for probability of subsequent visits of these balls. Okay. And what is the question? Suppose we have a random process in dimension 3 or 2. This random process is X, and we are looking for such probability that there exists the sequence of random times which are ordered in non-decreasing order, such that xt1, tau1 belongs to bu1 epsilon, xt2 tau2 belongs to bu2 epsilon, and so on. X tau n belongs to bun epsilon. It occurs that for Brownian motion, such asymptotics can be found, and it was presented maybe exactly a year ago by Kingston on our seminar. It was the investigation was based on the potential theory for Brownian motion, and the formula became very nice asymptotically. That asymptotically we get the 1 divided by the length of the edge of the polygonal line multiplied by epsilon in d minus 2 power. So it was very nice asymptotic. And the question is what we can do when the process X has no Markov property at all. So when we cannot use potential theory, which processes we will study? We will study the Stillhausen process, but without Markov property. We will study case when X is an integrator.
Is n fixed, Andrey Anatольевич?
Yeah.
N is fixed, and we send epsilon to 0.
Yes, it was the idea because you see, let us came to the picture again. It reflects that when epsilon tends to 0, then we can say that our polygonal line almost is inscribed in the trajectory, that it is approximated by trajectory. Yes. So we were looking for those for such asymptotic in the talk of Kingston, which I mentioned.
Okay,
but now we just concentrate on the following question: how just calculate or estimate this probability in case when X has no Markov property. So now I am not saying that we will push epsilon to 0. Just look for this probability. Let epsilon be fixed. U1, UN are also fixed, and X is Gaussian process. Yeah. I must say that some cases related to Gaussian visits of different domains were studied by Vladimir Ulyanov. But his approach is very different, and he did not study such problem as is written there. We discussed this with him, but without any positive conclusions, yeah, unfortunately. Okay, so the question is the following: what we can do with the following probability when X is just a Gaussian process without even Markov property? And I will consider the case when X is an integrator. What is this? The integrator is a class of Gaussian random processes were introduced by me in this paper, Stochastic Integration and Class of Gaussian Random Processes in Ukrainian Mathematical Journal in 1998, due to its good properties relatively to stochastic integration. We will mention the stochastic integration today, and even the Ito formula was proved there, and so on. But it occurs that the integrator are so good that we will be able to study the mentioned probability. The definition of integrator is very simple. So the centered Gaussian process xt is an integrator if there exists such positive constant c that for any n and any partition, deterministic partition of the interval 0, 1 and constant c0, cn minus 1 from R, the expectation of the sum from k equals 0 to n minus 1 ck delta x tk in square is less than c multiply on the sum from k equals 0 to n minus 1 ck square delta tk. This expression, this inequality means that at least step functions can be integrated over our process with some good estimation. Of course, if we have step function, we can integrate it over any process. But after this, we always want to have some limits of the step function and so on. So we need some estimation. So we just postulate, okay, let this estimation exist, at least for non-random step function. By the way, let me emphasize here that if we will require the same condition, but for random partitions organized by the stopping times and the correspondingly adapted random variables ck, so we just integrate adapted step function with respect to x. Then, if we have such inequality, it will mean that, of course, we must have expectations in right part. From this inequality, it will follow that x is a semi-Martingale. But now we just require this inequality only for deterministic step function, and it was checked in those articles which I mentioned that in this case the process X even can be non-semi-Martingale, so it can have no quadratic variation. Okay. So this is sufficiently wide class of integrators. Let me say that every smooth process is an integrator. Brownian motion, Brownian bridge, fractal for Curtin-Hurst parameters are also integrators. And the question is how to find probability when X is an integrator. The answer came from the structure of integrators. The following lemma was proved in those my article, and this lemma looks like X, the centered Gaussian process xt is an integrator if and only if there exists operator Q, which is linear and continuous, in the space of in the square integrable random functions L201 and Gaussian white noise psi in this L201. So one can just think about psi as about formal derivative of some standard Wiener process Wt, such that for all t, xt is equal to psi from q applied to the indicator of 0, 0t. By the way, if Q is just identity operator, we get Wiener process itself. So we have such a nice representation of integrator. The set of integrators is in one-to-one correspondence with the continuous linear operators in L201. But of course, the structure of a linear operator in the infinite-dimensional Hilbert space can be very complicated. This is the reason why we can construct such operator Q, even it will be projection, that X is not semi-martingale, for example. Let's go further and now I'm I'm supposing that norm operator norm of our operator Q is less or equal than 1. It occurs that in this case, integrator can be expanded to Wiener process with the help of new independent integrator. So let us define the new operator Q prime such that it is equal to square root of Q star multiplied by Q. The inequality that operator norm of Q is less or equal than 1 give us possibility to say that the difference of identity operator E minus Q star multiplied Q is a non-negative self-adjoint operator, and one can define square root using the spectral theory. So we have this Q prime. One can define a new integrator, but I use new white noise, just psi prime, which is independent from the initial one. So I constructed with the help of another Wiener process, which is independent from the previous one. And then for all H from our Hilbert space, here I use notation H sometime. This is the set of L201. I just use notation H for simplicity. So we have this relation because of independence and properties of white noise trivially. So it means that one can define new white noise, psi with tilde by this formula. And now one can define a new Wiener process related to this white noise. And by the way, this Wiener process W with tilde is equal xt plus x prime t, where t belongs to 0, 1, and x prime is also integrated. So what we construct? We just able to construct for any integrator another one which is independent, such that their sum is the standard Wiener. And it is a good news. We will use it in our calculations. How? Let me present you very simple example, but this example has two advantages. First of all, this example will give us an idea how to proceed in general case. And other, it is simple, and everybody can check it by hands very easy. So let us consider two standard Gaussian random variables which are independent. I will suppose that I have two positive numbers, alpha and beta, such that the sum of squares equal to 1. Define new standard Gaussian random variable xi, which is a sum alpha xi1 plus beta xi2. Suppose now that f, which is the function, has a following expansion in a series of Hermite polynomials. Here I say that f of xi is sum from n0 to infinity an hn xi, where hn psi is Hermite polynomial with the first coefficient equal to 1. It is just for convenience. Yeah? And this is a precise formula for Hermite polynomials with the main coefficient equal to 1. The question is, how to find such expectation? Yeah? Where f, we need to find expectation f of alpha xi. Of course, if we have the function f, which is defined by the formula, for example, f of x is equal sine of x, or f of x is equal x cubed, yeah, then the answer is trivial. But let's imagine that you just have these coefficients an. The equation becomes to be less trivial. And the approach can be following. Note that normally this this expectation can be calculated as follows. Let us calculate expectation of alpha xi1 plus beta xi2 conditionally with respect to xi2. Then we know that due to the independency of xi1 and xi2, this expectation must be calculated as follows. We just have to fix this one and suppose that it is equal to some y, then calculate obtained expectation with respect to xi1, and then put xi2 equal to y. Yes, this is the usual way how to manage this conditional expectation because it is very, very simple. It consists of independent parts. But now I'm just xi2 equal to 0. So this is the idea. But it occurs that conditional expectation of the Hermite polynomials is calculated very easy. So this is the answer. Suppose that you have a Hermite polynomial of degree n from this alpha xi1 plus beta xi2 from standard Gaussian, yeah? And you just calculate this conditional expectation, the answer is following. Beta n multiply hn xi2. Hermite polynomials are not only very good from the point of view of orthogonal structure. We all everybody knows that they organize orthogonal basis in the space of functionals from standard Gaussian random variable. But they are also very convenient when we calculate conditional expectation. You see, you have here beta in n power. Hence, one can say that our expectation is equal to sum from n equals 0 to infinity beta n an h n xi2, and finally we have the answer in terms of coefficients of expansion of the function f onto the series from Hermite polynomials. This is the answer, beta in n power an and h n 0. Moreover, one can easily calculate h in 0 by using, for example, the exponential generated function for Hermite polynomials. Let's do this, and we get the final answer. This is the final answer. This is the sum from L0 equal to 0 to infinity, minus 1 in L power beta 2L, A to L, and 2L minus 1 to factorial.
Andrey Anatolyevich, I'm sorry, I don't understand this expectation of f of alpha xi1 depends on beta. Beta is square root of 1 minus alpha squared, or what?
Yes, yes, exactly, because they are connected, of course. Yes, of course, yeah. So beta is square root of 1 minus alpha squared. Yeah.
And could you please repeat, how do you calculate how the first formula yields the second one? When you have expansion beta to the power n, an, hn of xi2.
Yes. This I have from this formula. Here is the reason, this one. And this formula can be easily obtained when you calculate the following. We know that if we consider lambda multiply on xi minus lambda square over 2, then it is equal to the sum from n equals 0 to infinity. Here we must have lambda n over n factorial hn from xi, yes? So to calculate this one, it is enough to know how to calculate this condition expectation. Yeah. And then you just use the fact that alpha square plus beta square is equal to 1, and independency of these two standard Gaussian variables. And by the way, this is a stochastic exponent. Its expectation is equal to 1. So this is the idea. And by the way, we get the following formula, where this is the answer. This is the answer for our expectation in terms of coefficients of expansion of our initial function into the series of Hermite polynomials. Of course, here I used some agreement. Let me tell you. Here I suppose that when L equal to 0, this minus 1 to factorial is equal to 1, because it can be expressed as 2 multiplied by 0 factorial divided by 0 factorial, and here is 2 and 0 power. But this is just agreement, and this is joke explanation why. Okay. So this formula can be checked easily, noting that here is the explanation, by the way, how to check, how to find the value, the conditional expectation of Hn. Okay. So the idea is following. Let us use the same approach for hidden probabilities for integrators. Let us try to do this. Where we have in stochastic analysis the operation of multiplication of coefficients on something. It is exactly the second quantization operation from stochastic analysis. So let us go to the general case. I am considering here the following. Let us consider gamma q. So gamma q, this is an operator of second quantization related to our supplement integrator. We just take this conditional expectation because the operator of the second quantization is the conditional expectation, which we actually need. And then if we will be able to get its Ito-Wiener expansion, the members of its Ito-Wiener expansion, then let us calculate the value of the last series when W dot here is equal to 0. Let me emphasize that values of Ito-Wiener expansion are the infinite dimensional Hermite polynomials. So this is not simply a multilinear form where we substitute some random element. Because in those cases, when W dot is equal to 0, evidently AN is equal to 0. But let's keep in mind that this AN is analog of a Hermite polynomial of degree n. And we just have seen that its value when argument is equal to 0 is not necessarily equal to 0. So we need to do several steps. We need to calculate this conditional expectation, application of second quantization operator, and we need to find the kernels of AN and then its values at the point 0. Let me say a few words about values at the point 0. So note that if n is of the kind 2k plus 1, then this guy an is equal to 0 at the point when xi is equal to 0. It reflects the fact that if we have the Hermite polynomials of such degree, then its value at 0 is 0. But what happens when we have such degree, 2k? In this case, we have a very nice formula for its value at 0, which contains so-called traces of our bilinear or multilinear form. These coefficients came from values at the point 0 of Hermite polynomials. These coefficients came from symmetricity of AN with respect to permutation of all coordinates, and we just have to choose such 2L1 and 2Lj. And here we have 2, because we have to choose which coordinate will be equal, and we have so many choices. And finally, trace. And what is trace? This is as usual trace when we just have a sum where some element of orthogonal basis coincide. You see here 2L1 elements indexed by I1, and so on, 2Lj in the various indices by this. So this is a multiple trace of our multilinear form, and it is reasonable. For example, when n equal to 2, then when we consider the kernel, so we have calculate only one diagonal. But when n will be 4, 6, 8, and greater, then we have a lot of diagonals. Yeah, a lot of diagonals. Of course, one can stop me and ask. We know from the functional analysis that not every operator, not every bilinear form has a trace. So what to do? What we know definitely about AN, that it is a Hilbert. So of course it can happen that it has no trace. And actually the reason why we can apply this approach, have to apply this approach very carefully, is that we calculate conditional expectation in infinite dimensional case. So we have to be careful with the limit, with the limits. But one can guarantee that this trace is finite, but by the following reason. You see, our an will be equal to the following. This is the result of the second quantization. We just put inside of the initial kernels of Ito-Wiener expansion, we put inside this operator Q. So after we have such expression, then let me say that the finiteness of the trace can be guaranteed by several reasons. One reason, Bn itself can be good, can be nuclear. For example, we remember that in case of integral kernel of multiplicity 2, if it is continuous, then it has trace. Second reason, which is much more wide for application, is the following. If Q is Hilbert-Schmidt, then the composition B and Q is nuclear already, and all traces will exist. So we have several possibilities how to say that, okay, our Q is such that for sure we have our multilinear form such that we can calculate all traces. Okay. So now how to find this one gamma Q from the indicator that Wiener process, initial Wiener process will hit, oh, by the way, here is mistake, will hit, here is UN, will hit as our balls. So let us recall that it was proved in my paper, smoothing problem in anticipated scenario, in Ukrainian Mathematical Journal, volume 57 in 2005, number 9, that second quantization of the functions from diffusion process satisfies some stochastic partial differential equations with anticipated stochastic integral. So we can try to use the same. I must say that this is not only one, but still it is a value. And why I am going by this way? Because actually this shows us that anticipating stochastic integral with respect to integrator and with respect to the initial Wiener process, which was for Wiener process introduced by Skorokhod, has meaning, has mathematical meaning. Because when we just say, okay, we construct some anticipating stochastic integral. For example, a Stratonovich integral, yes, when we have semi-martingale, or some other, the question naturally arises, why do we need this new construction? What physical or mathematical reasons are to study this new construction? And natural answer is there are some applications. Exactly as we have the fluidfulness of Ito theory, then we must find something where the extended stochastic integral or integral with respect to integrators arise naturally. And this is such place. We have with necessity exactly the stochastic integral with respect to integrators. Let us explain the idea. In case when we have just two times t1, tau1 and tau2, because we can go as we will see, we can go by induction. So let us start with these two times and then introduce such a function. This is an indicator that we have this new visit, tau 2, and this is a function of what? Of W sigma and sigma, where sigma is the first moment of the heating of the ball, U1 epsilon. Yeah. Actually, this function, this random function f, is nothing else than the indicator that starting from there, at this moment of the time, we will hit this ball B U2 epsilon. Then, actually, one can again explain this. And we need several definitions. So what I will do, I'm going to apply second quantization to this function, to this function from the Wiener process when it will hit the first ball. Let us consider just general. Suppose that nu is a random probability measure on some good complete separable metric space X rho and with Borel sigma field. Then gamma Q nu also is a random probability measure in the space. And even one can consider subprobability measure. So it can happen that nu from all x is less than 1. Example, if D is a domain in Rd, for x which belong to D, s belong to 0, 1, let's define tau xs, this is first hitting time to the boundary, and one can define the random measure as follows. It is it is concentrated on the boundary, yeah, and it is, oh, so let me say that here must be txs another one, and this, all this is in the denominator. Yeah. So now let us consider such a random measure, and one can consider the random continuous function such that is restriction on the interval T1 is measured with respect to increments of the Wiener process on this interval T1. This is exactly our situation because we just reach the boundary, we have checked the future of the Wiener process in order to understand will we reach another ball. And define now a weak integral from this function f with respect to this measure nu, excuse me, dv, dr, using the Fourier Wiener transform. Here, dv. What is the Fourier Wiener transform? This is a very powerful tool of this stochastic analysis. And I just recall that this is a expectation of the product of the random variable or random element on the stochastic exponent of the following kind in our case. So the definition of this random variable is the following. This such random variable.
I'm sorry.
Mhm.
Could you please explain a bit more? Because integrators for here is defined for random variables. Here you have a measure. New.
Yes, but you know, thank you. This is a good question because I forgot to say something about this explanation. I was going to say a few words, but forgot this. You see, here, when you consider new xs from some set, for example, delta, this is a random variable. And this, of course, is non-negative random variable. We know that the stochastic exponent, due to its expression, is also non-negative. So the product and expectation will be non-negative. And due to the back dominated convergence theorem, it will be additive.
Okay.
Yeah, you see. So
I
under fixed
understand now.
h, we have another measure, but this measure already is deterministic, but still measure. Okay.
Thank you.
Thank you for the question. I forgot to explain this. Yeah. Okay. So
You're welcome.
we have such definition, and there exists a very nice lemma now. This lemma reflects exactly the situation with the Ito integral, because I think that most of the audience of our seminar today remember the time when it was firstly discovered the Skorokhod integral coincide with Ito integral, in case when Ito integral is well defined for good integral. Here, exactly the same happened. Because you remember the properties of our nu and f. Nu is defined like about the past of Wiener process up to the heating moment. And f is defined like the future of Wiener process and after the moment. Of course, this is not a rigorous explanation, but this is just the idea why we can expect this. And rigorous explanation is following. Let us recall what is the Fourier-Wiener transform from other side, other point of view. Let me recall you. When we consider Fourier-Wiener transform, we just have the expectation of the product of alpha with this exponent. This is stochastic exponent, of course, but this is a density of shifted Wiener measure. So our Fourier Wiener transform is just expectation, here, just expectation of the shifted random variable. And then one can consider instead of W such random process, and of course it has a strong Markov property too, because H is deterministic. So we can use strong Markov property and get the desired formula. Now let us consider such expression. Here we use the usual approach when we want to calculate some probabilities related to the heating times of Wiener process. Let us include this probability in a much more general family where we introduce the dependence from the starting point and starting time, x and s. And here is our uxs, which is already gamma applied to this function f. F is heating probability to heat something else, or f is has just such properties that it is a measure of with respect to future increments of Wiener process. Then it occurs that we have such nice stochastic anticipating problem for our U, which has a usual part which came from Wiener process and unusual part which came from second quantization, where we have the extended or weak stochastic integral, which was defined by me with respect to this integrator zeta, where z is just second quantization of W. So one can consider such anticipating parabolic problem. Anticipation came here not from the idea that we have noise and time. No, we now, of course, have variable s which play a role of time. But now this zeta, as we said, cannot be semi-martingale at all. And UXS is not adapted to its filtration, but we have another kind of integral, and this is a reason why it is named anticipating stochastic integral, and all this problem is called by anticipating stochastic problem. So we have this problem. And now one can why, by the way, how we get this boundary condition. It reflects a very nice fact also, which was mentioned in my paper, that operator of second quantization have a very good relationship with weak product. Actually, it commutes with weak product, with extended stochastic integral. So one can proceed as follows. Yeah? And actually, we substitute this inside of us. Yeah. Okay. So now we also have to ask how we can solve this parabolic problem. Yes, it will give us the new probability, maybe, but how to solve it? And the solution is following. Let us use a Fourier-Wiener transform. Then it occurs again that we have a very good news that Fourier-Wiener transform react in a very nice way on anticipating stochastic integration. It looks like a usual Fourier transform react on the differentiation. It just gives us the argument. Here we have this one, QH from S. So here you see usual parabolic problem. You see usual parabolic problem. And it contains a main part which is very good. It is just from Fourier from Heat equation. So when a D has smooth boundary, one can use Duhamel series. One can use Duhamel series to get the Ito-Wiener expansion of this UXS, because what will be the Duhamel series? It will contain repeating integral containing QH S1, QH S2, and so on, green function related to the main part and domain D and its derivatives. That's all. So one can get the Ito-Wiener expansion for our problem. Then recall that Q can be Hilbert-Schmidt, but one can use the properties of the kernels of Ito-Wiener expansion. And surprisingly, but we studied the estimation of the kernels from Duhamel series in a paper which was defined to very different object, to the 1-point densities for Ratia flows with drift. But maybe the word drift explain why we get Duhamel series in those paper, but still we have a way how to find, at least as a series, the desired probability. That's all what I wanted to say. Thank you for attention. If there are some questions or comments, please.
So you can solve your problem about hitting these balls for integrators. You at first solve it for Wiener process, and then apply this theory with second quantization.
Actually, I use the solution for Wiener process here. Here is actually I don't use the obtained expression, final obtained expression for those probability, because when Kinson demonstrate its final formulas, it contains potentials related to Brownian motion. These potentials are already the integral from exponents. And in order to get Duhamel series, you have like rewrite those good integrals in a series. So here is the place where we use Brownian motion theory. Maybe it can be said that not Brownian motion, but just parabolic problem theory with a very good main part. Because if we have the answer for Brownian motion like probability is equal to, we cannot do anything with this. We have to begin to play much more early.
Andrey Yurievich, you are muted.
I have one more question. How did you guess the answer? So what was your way like this? You know the answer for Brownian motion, and then you have integrator. So if you formulate to write Radon-Nikodym density, which may not exist now.
Yes, it is.
And then integrate, and here Fourier-Wiener transform appears. So is it
no,
correct?
no, this is not the way. I don't know about the. Actually, I think that in most cases, distribution of integrators are always
Singular.
Yes, exactly, because it is Gaussian, even if you take Brownian bridge. Yeah? I think that only one case when Q is equal to identity is such. No, we don't use this.
Well, maybe you have Q identity plus something Hilbert-Schmidt.
No, maybe you are right, but I don't care about this. Yeah, I don't care about this.
Mm.
Yeah. So, as I said, Q can be a projection, for example, on infinitely dimensional space, and it can be constructed in such a way, this space, that we get non-semi-martingale at all.
And this function UXS, it is related to hitting one ball, yes?
Yes, exactly.
And then you will use some induction.
This function is related to hitting the first ball. Mm-hmm. Then this U with tilde is related to hitting this this is for the second ball, B U2. And this is for this D is like R D minus B1 epsilon, yeah.
So then iterator you can do further for More balls?
Yes, iteratively we will do this for finite number of balls. Yeah.
And as far as I understand, fractional Brownian motion with first parameter bigger
Oh,
than one half
yes,
is
yes,
an
it is.
integrator.
Oh, even Jana, I can to give you a formula already. So, so let me do this one. Okay, no, this is not this document. Okay, now I will find just document where we will find a precise formula for this. Let me do this.
Okay, probably later by email. Also.
Let me just say when it is an integrator. Yeah. So if we have the first if we have correlation function like let me t into alpha plus s into alpha minus t minus s into alpha, then for alpha which belongs to 1/2, then it is integrator.
Yeah, okay. Because the corresponding operator Q is the nice operator. Working nicely.
The corresponding operator is the kernel from the
Yeah, risk potential.
yes, alpha minus 1/2, t minus s alpha.
Yeah.
Okay.
Thank you.
Andrey, I would like also to ask a very short question. It is about the connection that you mentioned when we have a Gaussian process with this integrating property which you formulated. The result is that actually you can identify it, or there exists an operator Q which is non-random.
Yes. Let me.
It is at the beginning.
Yes. I remember. It's just. Yeah. Okay.
But if you would just forget about the Gaussian property, and then would be the statement like that correct, that there exists an operator Q such that Q of the indicator is measurable with respect to the sigma algebra generated by Brownian motion? I mean that you assume that Q of the indicator is good enough to be able to integrate with respect to Brownian motion. Would that you have a statement that by such an operators could be covered any process with this integrability condition which are measurable with respect to a sigma algebra generated by Brownian motion?
You see, the following answer can be done. You see, one can if the process X is not Gaussian, is non-Gaussian, but still measurable. Still, I will say in this W, then the integral with respect to X due to this inequality from deterministic function will be well defined. So we will have this integral as a random continuous in L2 sense functional on the space L201. Then it will be a random operator in a sense which I defined in my book. It will have e to Wiener expansion and representation more or less that you want. But the representation will be following. We will have a lot of e to Wiener terms Qn. They will depend on H, and they will depend. For example, you can put here this indicator, and here we will have xi. And of course, you can say that you can unite everything with respect to xi and just have an application of some random operator to our indicator 0, 0t. This is the answer.
Okay, nice. So for this interoperability condition, it is defines even the large class of processes, which is
Surely, you can check my book Random Maps and Stochastic Analysis in Hilbert Space exactly about this construction.
Okay, thank you.
I have a short question about a general question about the Ito-Wiener transform. Maybe I just forgot. Is there a way to reverse it?
This is a very large problem. And also in my book, in English version of my book, which is printed then, you can see that sometimes it can be possible. But even for very simple functionals, like we consider the solution of finite linear system of stochastic equation with extended stochastic integral, to have a backward expression, you must need backward mapping like Fourier transform. And it not always exists, and you have to find some Hermander step and so-called Hermander step and so on. So it is a very difficult question, and there are no any general formula which works for a large set of functionals.
So, thank you.
You're welcome. Okay, if there are no any other questions, then let us ask Georgi about next speaker. Who will be the next speaker?
Next speaker will be Ilya Pavlyukevich.
Okay.
With the talk energy balanced model with moving ice line.
Oh, very nice. Very nice. Okay. Thank you very much for attention and for the questions. And see you next week. Bye.
Okay, bye.